Everyone. Okay. Hi. Good morning, everyone. It's week 9. So this week we'll be talking about dynamic programming. I think it's one of my favorite topics actually, for some reason. I don't know why, but I just like dynamic programming. Okay. So anyway, let's begin. So I've started recording. All right. So this week's tutorial is straightforward in the sense that there's nothing detailed for me to go through. I'll just go through a little bit about like what DP is about, using how to use dynamic programming, and then we'll just be going through the tutorial questions all the way. So I think I'll try to focus more on the first question a bit, because trying to come up with recursive formulation for DP questions is important. So it's important that to get it right first. Okay, so let's begin. Admin matters, right? So just a reminder, because if we follow the 3230 lesson plan, the next lecture is on this thing called NP completeness reductions. So if you haven't been following lectures, I think it's pretty independent. So in the sense that, if you haven't been coming to the past 3 weeks, you can just go next week and hopefully things are fine. I will recommend try to attend them, because I think the content is pretty confusing and abstract. So let's just try your best even if you haven't been following the materials the past 3 weeks. Okay. Then the other thing is that I announced this in our class group, the Telegram group, but the tutorial videos I've started uploading them to YouTube, mostly because the features are nicer there. You can speed up 1.25, 1.75, and you can move forward and backwards pretty easily. They are in this playlist, which I sent to the class group as well. And whenever a new video becomes available, I'll just upload it to at least to this playlist. Okay, so let's begin with a little bit about background and motivation about DP. Okay, so maybe some of you might be thinking, like, why is it called dynamic programming? So it's by this guy called Richard Bellman. And okay, I don't think I'll go through everything here, but it just says that, he was doing research, and apparently like his Secretary of Defense hated the word research, but he needed a word, like a word. Can push it to like 5 times. Use JavaScript bookmarklets. Okay, I don't know why you said that, but use that to do what? Push to like 5 times plus plus. But anyway, so I think he was trying to come up with like this technique while trying to satisfy the Secretary of Defense hatred for the word research. So, well, he said it's to capture the time-varying aspect of the problem, which TBH, I still find it hard to see what he actually means, but nevertheless, like, apparently he also called it dynamic programming because it sounded impressive. So basically he thought it was cool. Okay, so at least that's the story, how the story goes. So don't think too much about the meaning of dynamic programming. Sometimes I still wonder like why, how to map it to the actual like what you are doing in dynamic programming. But never mind. So this is just trivia. So, but why learn dynamic programming, right? Like maybe you'll be thinking like, will I ever use dynamic programming? Okay, so to get into Google, maybe, right? So this is one of my friends. He's a Google intern. Some of you might know him, and he said that they did actually test him on DP. So maybe some of you who's going to interview with Google is gonna be asked DP questions. Who knows? I think last weekend was the Google intern online assessment, right? So hopefully it went well for some of you. Okay, so but the serious answer is because, well, DP is a design paradigm that can really improve solutions from exponential time to polynomial time. Like a simple example would be Fibonacci, right? But that's pretty trivial. But it's also a good candidate for you to try and solve optimization problems where you are asked to, hey, can you help me find the minimum of these things or find the maximum of that thing? Okay, and a lot of applications like content-aware image resizing, all-pair shortest path for routing, even like when you talk about computational biology, like trying to see whether 2 DNAs are similar, or even your autocorrect, it might have relations with this edit distance thing, or if you use Git, right? If you do Git diff, apparently there's relation with longest common subsequence as well. Okay, so there's a lot of applications of dynamic programming. All right. And here's one example, like there's this thing called content-aware seam carving. So it's like it try to squeeze the image, but it's aware of the content. So the image, you see like this castle over here doesn't get squashed, but rather they try to remove spaces from like the literal empty spaces. Okay, so if you're interested on what seam carving is, I thought this was pretty cool. If some of you took CS4230 computer vision, you might have seen this. It's just briefly mentioned by prof usually. But if you're interested to know a bit more, I've linked a lecture here by Blue Brown. I think he's a pretty famous YouTuber. Okay, so this is that, and okay, so never mind. This is just another trivia. Okay, now let's begin the class proper. That was just like a quick talk about what DP is about. Okay, so using dynamic programming. So when to use dynamic programming, it's when the problem kind of exhibit this optimal substructure. So it means that you try to break the bigger problem into something smaller, right? But that something smaller, right? If you get the optimal solution to the smaller problem, you can reconstruct the answer to the bigger problem. Okay, so it just means like you see all these small problems, you use the solution that you have to solve the smaller problems optimally, then you try to combine them together in some meaningful way, and it will solve your bigger sub problem. Okay, so usually the proof for this is so I just quickly mentioned, they usually say something like the cut and paste argument. If I were to go through it very quickly, it's something like usually cut and paste arguments are in the flavor of like you assume that you don't need the smaller sum problem to be solved optimally, right? So if you don't need the smaller sub problem to be solved optimally, you claim that you can have an optimal solution to the bigger problem. However, if you replace that smaller sub problem that you didn't solve optimally with a solution that you solve optimally, somehow you get a better result, resulting in a contradiction. Like that's usually the cut and paste argument, how it goes like in the flavor. But I won't go through it too much in details at least for this tutorial. I might talk about it during consultations. Okay, so and then if it has overlapping sub problems, like for example, this sub problem over here is used by other multiple sub problems. So it's used multiple times. It'll be good if we can store the result somewhere. Okay, some of you might be aware of the term memoization already, right? So memorize, not memorize, but memorize, as in like making a memo. So memoization. So that's a good time for you to think about DP as well. Okay, then one important thing is that the dependency between the sub problems is acyclic, meaning like if you solve this sub problem TA, for example, right? It depends on maybe TD. But this TD shouldn't depend on TA, because this is what we are trying to compute. We're trying to compute the sub problem TA. How can it like compute itself if it needs to know about the answer to itself? Okay, that's why we need the dependency to be directed acyclic. Most of the time, at least the DP problems that I know of are pretty like you don't need to think too much about the acyclic about this dependency. But on some problems, I think especially graph problems, if you kind of like try to DP on a graph, it can be kind of like it can be cyclic. Okay, so how to DP, right? The essence of DP is actually kind of like brute forcing, but trying to do the brute force carefully. Okay, it sounds a bit abstract now. We'll see that a bit later. So the first thing you have to do, like the important step of trying to do a DP, is to identify what are the sub problems. Like how do you frame the question to see the different sub problems? Okay, try to identify the different sub problems, because for most questions you might have seen up to now, the sub problem is pretty trivial in the sense that it's obvious that that's the only thing that you can do usually. But I think some advanced questions have different ways that you can see the problem, right? Then depending on the way you see the sub problem, the time complexity changes. Okay, so then this is like one thinking. So if you took CS1101S under Prof. Martin Hans, you might have heard of this term called wishful thinking, but it just means that you assume that you wish that you have solved the smaller sub problem. Like somehow you know the result already. Okay, if you know the result of the small sub problem, can you use it to solve the current problem that you're solving. Okay, we will try to see that again later. And the tip to do this step is that don't try to unroll the recursion, because dynamic programming recursive formulation is usually like in terms of maybe like express this as the small sub problem, right? You try to think of the sub problem, don't go even further and try to think of the even smaller sub problem. Just stop at one level, stop at the next level, assume that you have the result at that next level, and then use that result. Okay, then after that, you try to come up with a relation, as I mentioned before, right? Try to guess like how are the two things related. Okay, you might not know. Maybe there are a lot of sub problems, small sub problems that you have. There are a lot of sub problems that you have, and maybe you don't know which one to use, right? So if you don't know which one to use, guess them all. Okay, try all the sub problems. Okay, remember this is kind of like BP, it's kind of like brute forcing, but carefully. Okay, so you use you brute force, kind of like the brute force aspect is trying the all sub problems part. Okay, and remember, because a sub problem result might be reused, so we store it in a table, right? So like the bottom up dynamic programming or memoization, you just have a table and then store it there. And the time complexity is the total time that you take to compute all the sub problems. Okay, any questions about this so far, like how to DP? It's kind of abstract now, so maybe you might see this more later, but maybe a short mention is that it's the time compute all sub problem. Usually I see something like time per something like time per sub problem total times total number of sub problems. Total number of sub problems. So usually I think in lecture, prof would mention something like this. So total time is the time per sub problems times the total, how many problems are there, right? This is not exactly wrong, but in some problems, I've actually seen problems where the sub problems have different time complexity to compute, like actually different time complexity, and it matters if you only take the upper bound. Okay, like graph problems actually. So like more accurately, it's more like to compute every single sub problem. Like you see the individual cell and add them up. Like this is the more accurate time actually. Okay, that's just a brief mention. But for most problems, the time per sub problem times the total number of problems is fine. Okay, all right. So if there are no questions, let's begin with this tutorial where like the tutorial questions proper. So the first question about this convex polygon thingy, it sounds very cheap. And I just want to take note in my slides, I kind of unintentionally use clockwise to order the points, but the tutorial slides use counterclockwise. So just a quick note in case you might be confused from the difference. Okay, so apologies for the difference. But okay, so we start off with this thing called a convex polygon, represented by several points stored in the array. So points P1, P2, all the way to Pn. It represents this thing. Just think of it abstractly. Don't need to think too hard or like, oh, how exactly is this represented? Are they like coordinates or whatever? Don't need to think about it. Just know that some representation of point. Then, okay, so today we'll deal with convex polygons, which look more like this. We don't deal with what we call the concave polygons, so don't need to think about these kind of cases. So in the convex polygon, every angle is like less than 180 degrees. Okay, so then here's another definition. If I have Pi to Pk, that means we only consider the polygon of this form. Okay, Pi to Pk, polygon consisting of Pi to Pk. Okay, so the weight of the triangle, right? So you form this triangle. If you form the triangle using the sides ijk, you try to draw a triangle. The W of ijk is called the weight of the triangle. Okay, assuming it takes O1 to compute. So we assume we can compute this in O1 time, right? And the total cost of triangulation is basically for every side, you kind of make triangles for them. Okay, you make triangles for them, and this is the total cost of triangulation. And there are different kinds of triangulation, like maybe this, for example, right? You can see that there are different ways for you to triangulate this convex polygon. Okay, so um, the classic definition of the weight, right, is usually the length of the triangle edges. So basically the perimeter of the triangle. You try to minimize the perimeter of a triangle. This is a classic definition of the weight. So, but well, here's another example. Like we are in the COVID season, right? So maybe a motivation for weight is that it's kind of like we wanna see how close people are to each other within a room. Like this here, over here, I have 3 different people in a room, and well, the weights are 0 maybe for everything because they are not close. They are all in different rooms. But the weight of this case over here, because they are in the same room, then maybe it contributes to the weight. So we want to minimize like interaction between people. Maybe this is like a possible interpretation of the weight, but this is just like to motivate it a little bit. But in computer graphics, I believe that triangles are often used to approximate smoothness of surfaces. So, well, if you're interested to find out like, oh, why do we care so much about triangulation? Maybe you can look at graphics. I have never taken graphics before. This is what my friends told me. Okay, so going forward, but given this polygon, right, the question wants you to try to minimize the total sum, the total cost of triangulating the convex polygon. Okay, and let Cij, and I think the tutorial slide uses tau ij. I think scary symbols are scary, so let me just put C for cost. So let Cij be the cost of triangulating, like starting from I to J, right? So I to J, so maybe something like this over here. Okay, so what we want you to do at first is to write down the recursive formula for the above problem. It's implying that we can do dp, but how do we do dp? Okay, and it's trying to express, basically try to express Cij in terms of Ci prime J prime, where Ci prime J prime represents smaller polygon. So for example, C1n looks like this, right? C1n looks like this. Then maybe you claim that, oh, the optimal sub problem is actually like relating Ci to Ck and Ck to Ci, maybe, for example. Okay, so this is the question. Is it confusing? I'll give some time to fill in archipelago. Okay, but is it confusing? Any questions? I know it might be scary. You see pictures now. Usually you don't. Now there's some geometry involved. Mhm. Okay, nice. Okay, let's resume at like say 9:24. 9:24. Nice. If you don't know, just put don't know, like usual. Or if you confused about what DP or what I'm even asking, just let me know. I must admit this question might be harder to see. It's like interesting DP problem. So Okay, so I think I'll resume because it might take some time for me to go through the this thing. All right. So remember, right? So as I mentioned earlier, we are trying to brute force, but carefully. So first, really try to identify which sub problem is. Try to guess. Like how can you break it apart? Like when you see this convex polygon, how do you break them apart to get the smaller polygons? Okay. Usually when I think of dynamic programming, I immediately think, how can I like make this problem even smaller? So from a big polygon, I try to make a smaller polygon and try to make a meaningful relationship between them. Okay, so here's the idea. We identify the sub-problems, and at least they are nice enough to tell us that okay, how you calculate the sub-problem is consider Cij, which is starting from I to like go clockwise until you see J, and that's the polygon. Okay, so assume you have solved the smaller sub-problem, right? So this is like saying, okay, assume that you know that this is Ci to K, this is 10, then this is like 30, for example. Okay, so if I know that this polygon takes 10 and this polygon takes 30, do we know how to compute the entire thing? Okay, so that's kind of like what I mean by assuming that we know the answer to the sub problem without thinking even further, without unrolling the recursion. So which sub problems are appropriate? And take note, we must cover all the possible triangulation. Like we must not miss a triangulation. And the idea is that you try to guess where the triangle with side PI, PN should be. Okay, because if you want to triangulate this entire thing, there must be one of the triangle happening. Like maybe this triangle must have happened, right? Based on the edge, based on this side, P1 to Pn. Okay, one of these things must have happened. So try to guess where it should be. Because if you have this side, P1 to Pn, it could be here, right? Like a possible triangle is that it forms this triangle. Or 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 it forms this triangle, and so on, right? So there are multiple triangles, right? So wait. Okay, so if I have guessed a triangle, right? For example, this position over here, I've guessed PI, PJ, PK to be the triangle we are at, right? Let's say this is the answer. How do I compute the total sum of the total triangulation? So I'm not going to talk about minimum yet. I'm just gonna ask like, oh, if I break it like this, how do I compute the cost of triangulating the entire thing? Okay, and the answer is you consider, okay, so the red part is you consider this weight, right? So let's say you know the answer to this weight already, because we can compute it in O1 time based on our assumption. Then you consider this sub problem. This is sub problem 1, and this is sub problem 2, right? So this is consider a smaller case. Okay, anyone confused by this diagram so far? Okay, this is just after making a guess of where that triangle should be, we try to see how do we compute the cost of triangulating this entire thing. Computing the cost for this particular polygon with this red triangle. This is just for one. Okay. I'll stop for like 10 seconds for confusion maybe.
Yes. How come it's CIK plus the weight of IKJ and then CKI? Isn't it CKJ?
Okay, thanks. I think I made a typo. Yes, CKJ. Thanks a lot. Yeah, thanks a lot. Yeah. So there was a mistake on my part, my bad. Then okay. So right. So I'll go on, and the question is like which triangle to use. We have so many triangles to consider, right? Like any one of them could give us the minimum, right? You have all these very nicely illustrated triangles. I think they look pretty aesthetically pleasing, but which triangle to use? That's the question. And well, you don't know which one to use because any of them could be the best, could be the one that gives you the minimum. Okay, and so if you don't know which one to use, try them all. try all the sub problems. Okay, and this is like kind of maybe why I like dynamic programming, because it makes me lazy. I just need to think of the sub problems. I don't know which one to use. Just try everything. Okay, so try them all. So meaning that among, so okay, so this is a typo, right? So this is J. This is J. So for every K, right? So every K, for all K, meaning all these points, 1, 2, 3, 4, 5, 6, 7. We try for everything. We try this recurrence relation. And then we take the minimum of everything. Take the minimum of everything. I won't talk about the base case yet, but are we clear on this formulation? Like how come I consider everything? Because there are a lot of triangles, There are a lot of triangles, and I don't know which one is the best. So I don't know which one is the best. Let me try everything. Okay. So this is the recursive part of the recursive formulation, and some of you actually got it. That's cool. That's great. Okay. Then the base case is basically when you recurse to only like something of like something like this, you know, like they are neighbors, the points are neighbors. Clearly the weight is 0, right? It's not even a triangle. So the weight is 0. And so this is the, okay, so this is the recursive formulation for this question. Any questions? This part is important because it'll motivate the next part. And the funny thing is, like, I don't know why the third question gave out a question 2 where the algorithm uses this recursive formulation. But do you understand why it came from? Okay, so some of you might have alternative solutions. Okay, if you have any question, just shoot out in the chat. Okay, so some of you might have alternative formulations. Like there are many ways to formulate it. So let me go through one. Basically, I propose a new way to divide the answer. Okay, I say that, okay, choose a point, choose an anchor point. I choose one over here. Just now I tried all triangles. Now I try to get all the dividing lines. Basically, starting from here, let me divide into this part. These by these lines. Meaning for one sub problem, for one case, right? I just compute from I just compute Cij plus Cji. This is all I do. Then I try to find the cost for every division. So I try for all like j, basically all the j going around lah. So I won't write that formally. Okay, so looks similar, right? Looks similar. And so, but this is actually not right. Okay, so I wanted to give time for you to think whether it's correct or not, but I spoiled the answer. But it does not cover all possible triangulation. And here's like a counter example. If you just have a square, if you just have a plain square like this, just take this point. Remember, my algorithm is to just take this point and draw everything starting from that point. I'm actually missing the symmetric case because I'm not trying another possible like starting point. Okay, so it does not cover this case at all. So it could be that this is the best triangulation for some reason, right? But it doesn't cover it. So our solution will not even look at this particular case. So I don't think this possible alternative works. Okay. So this is just me telling you that, hey, there are different ways you can try to think of sub problems, but however, there are things that do not work as well. Okay, so you have to think carefully whether it works or not. Okay, I have several more alternatives actually. I had fun thinking of them, but let's not do that today. I think I'm slightly later than I had expected. But the lesson to learn here is that there are different possible ways you can divide the sub problems. Like I gave you an alternative, right? Thinking of the sub problems differently, but you can be wrong because there might be some cases that you do not cover. So you have to be careful and try to think harder whether it's actually correct or not. For our case, the reasoning is more like, if you imagine one side, you must have formed triangle with like some other point, right? So you try to guess where that triangle could have formed. Whereas in the line alternative that was wrong just now, well, by drawing single lines, it doesn't tell you about like how you form the triangle with that side. So it's kind of like the intuitive reasoning for that. Okay, and some are more efficient than the other. I propose something that works but is slower in one of the alternatives, but maybe we can go through that later. So basically, try to see whether you can account for everything. In some cases, like if this week you went to the greedy algorithm lecture, you might not need to account for all the possibilities. Maybe you can just show that you can make a greedy choice, right? And that is sufficient. You don't have to try every sub problem. Okay, so in that case, that will be like a greedy algorithm question rather than DP, usually. Okay, I'll go to the second question, but any questions about how I form the recursive relation, like recurrence relation here? Because it's important that you understand how this works for the following questions. And just remind again, this should be J. Okay, I'll stop for 20 seconds maybe, because it is just that important. Okay, no one asking, so I'll go on. Okay, the next question, which I also let you to time to fill an archipelago, is you're given this algorithm to compute the cost, right? In tutorial, it says like find tau or something, but tau is fancy, so I just call it compute cost. But what it does, right, is basically it literally computes what we propose, the recursive formulation that we proposed, using and well, this is exactly what I showed you, right? The recurrence. Find the minimum over all the compute cost of IK, the weight of IKJ, and then compute cost of KJ. And okay, luckily I didn't make a typo here. This is literally what they are doing. Okay, so just try to fill in the archipelago to think like what's the running time of this. Shouldn't be too hard, I guess. But showing why exactly it's 2 OIJ might be trickier. So maybe let's resume at 9:38. Okay, how many people are online? Okay, so I'll go on. Okay, majority of you got it right. Of course, it's exponential to power OJ minus I. And here's like one way you can prove it. So let the Tn be the running time for n points for you to compute 1 to n. Okay, so base case, which is you only have 2 points, that's C. Like let's say it's like constant. Okay, so Tn, I define Tn to be for the running time for a polygon if you consider n points. Okay, so Tn is all of this thing, right? It's T2 plus Tn minus 1. Okay, so it's this is T2 times n minus 1, then T3, a polygon with 3 points, and n minus 2, and so on, right? So you increasingly increase the size of the polygon on one side and decrease it on the other. Okay. This might take a bit of thinking for you to get through, like if you try to come up with this yourself. Then notice like, oh, this one is like for you, as you go down, well, the size increases, right? Because you can imagine rotating the triangle, you rotate the triangle and the polygon gets bigger on one side and it gets smaller on the other. So this is the two thing. And well, notice that they're actually kind of like symmetrical. There's T2 on one side, also T2 on the other one, right? So basically every of these sub-problems appears twice. They appear twice. So it can be simplified to Tn equals to 2 times the summation of everything plus C times n minus 2. N minus 2 because there are n minus 2 of these sub times we are computing this. Okay, so let me know if you have any questions about how I got from here to here. If not, I'll go to the next slide. So now our goal is to compute Tn, but it has this monstrosity of summation of recurrences. Okay, and like don't try to draw the recursion tree for all this. Okay, Tn equals to like this plus that plus that plus that. You're gonna have a lot of sub problems. Here's a hack. A hack if you see like a summation of sub problems, you consider the smaller one. Consider n minus 1, right? Consider a smaller version of it. Consider a smaller version of it. So it ranges from I to 2 to n minus 2. It just has one or rather two less sub TIs to compute. Okay, and then you subtract them. So this is a hack for you to cancel off all the sums. Okay, so basically earlier you had something like, you had like t whatever times t whatever. Then this, in the n minus 1 case, you only have this much, t whatever. So by subtracting off, you kind of like delete this part and only keep this t. Let's call it TA. So that's what's happening here. Okay, so it's a hack if you have summation of sub problems. So just do this. Then you rearranging, you get Tn equals to 3Tn minus 1 plus C. This is much more manageable for you to use recursion tree rather than like this thing over here, isn't it? Okay, so with this, well, the running time of this, I won't go through too long. You should know by now, or should be able to solve by now. It's something like O3 power n, which is well exponential. The point of this question is that you get exponential time to solve this problem, which is bad. Okay, we want to solve it efficiently, but naive algorithm, just formulating the recursive formulation without doing anything fancy, will give us exponential runtime, and that's bad. And the fundamental reason is because we use the sub problems repeatedly. We keep recomputing the sub problems, although we have computed them before. Okay, any questions about the math? And frankly speaking, the math should not be the focus of this tutorial. This question is just to show, be careful when you do DP. You need to tabulate. Don't recursively formulate and call it a day. You need to memorize. Okay, so question 3, the triangulation sub problems. I'll just go on. So now it tells you this, right? So this algorithm, they want you to answer questions about how many sub problems are there and like maybe the time taken to solve it. So what do you think? Fill in archipelago. So take note, this is not the runtime. It's asking how many different compute costs ij are there. How many different compute costs ij are there? Or like how many times do we call this? No, sorry, not how many times. How many different compute costs ij do we call? Okay, so let's resume at 9:45. Let me say earlier, because there's the last question which is slightly harder. Okay, I think I'll go on. So in the interest of time, all right. So the answer here is 3. There are at most n squared different subproblems, and the reason is because okay, you can try to like imagine it. You can try to imagine the recursion tree, right? So if you imagine like T14, basically polygon from side point 1 to point 4, if you recurse, you kind of like go in this direction. This is expansion of the recursion tree until you reach the base case. And just trust me on this, there are actually 6 distinct subproblems here. Okay, actually it's not hard to count, but trust on me on the recursion tree. If I make typos, apologies. And there are 6 distinct subproblems, and that's like 4 choose 2, right? 4 choose 2. So in general, there are n choose 2 subproblems. Basically, you choose all the pairs of i's and j's. Okay, all the different pairs of i's and j's where I is less than j. Like usually this is the definition of pairs. So just recall, n choose 2 is less than n squared. N choose 2 is less than n squared. So there are at most n squared different subproblems. Why number 2 is wrong is because it says it's at least exponential time to compute each subproblem. It's not exactly, which we'll see in a bit. Okay, so I think we'll see in a bit, but never mind. So anyway, the point is that there are n square subproblems, and we compute each of them multiple times. Okay, so final question, bottom-up triangulation. And I see some answers saying that actually the one in the tutorial is movable. So that's kind of like a hack. But anyway, try to think of a way. So basically, what happened all this while is that we formulated from top down, right? From top down, we look down. We recursively form a subproblem. What this question is asking is that, hey, let me create a two-dimensional table. Can you try to fill up the values starting from like the small ones, the base case, up until the value that you want, T1n. Try to fill it up like iteratively from bottom up. Okay. So I expect a lot of not sure's, but I'll give you some time to think about it. So let's say 9:48. 9:48 resume. Okay, nice. Okay, so I see a lot of people having no idea, and yeah, I think let me just go through it, because if I wait for too long, then everyone will say no idea, and it's okay. So the goal of this question is that we want to find value of Cij, and we want it to run in On cube time. So it tells you, okay, using On cube time, we can solve the problem. And remember, it computes only at most n square different subproblems, each of them exactly once, meaning we just retrieve it from the table. Okay, it should give us a clue of the time taken for one subproblem, which is On. Okay, each subproblem should take On time, right, for us to get On cube runtime. So here's the thing. So like, if I have no idea how to do bottom-up dynamic programming, I try to like visualize the table. Like, how do I want the table to be? We'll try to do an intuition later. Okay, so but just visualizing the table, Ti to Ti plus I plus 1 is basically this diagonal of the table. Okay, so take like 5 seconds to verify that this is indeed the diagonal of the table. Okay, and our goal is this value over here, T1n. Is this goal? This is our goal over here. All right. So, well, if you think about it, if you think about in terms of the table sense, right, you try to go diagonally from this diagonal, go up diagonally until you reach this guy over here. Okay. So, like perhaps there's an approach. So, how do I compute a cell? Right? Remember, a cell is like T13. This is basically computing from you have 3 points, then you go compute them like that. Okay. So, well, for the base case, for this case over here, I mean, you can see it's a triangle, but in our algorithm, it's basically, this is exactly what we have before, right? Our recursive formulation. It was the CIK plus CKJ plus W of IKJ. This is exactly what we had before. Okay, that's how you compute a cell. Okay. Wait, did I miss a slide? I think I missed. Okay, I think I accidentally rearranged the slide. But anyway, here's another one. So you have T14, right? You have this guy over here. To compute this guy, you need to compute this plus this is this one over here. Okay, plus the weight 1, 2, 4. And another one that you compute is this guy and this guy, which is this one over here. This is following our recursion, our formulation. Okay, so with that in mind, so this inner loop over here for I less than k less than j, it is exactly changing all the k in between is 4. Okay, so the changing of the k is precisely for you to compute all these things, all these values over here. Okay, so the question is, okay, so here's another example how the recursion looks like. So for this guy over here, right, in terms of the table, if you're computing T1n, how you compute T1n is you take this cell plus this cell, or you take the next loop computes this cell and this cell. The next iteration of the loop computes this cell and this cell, and the next iteration of the loop computes like this cell and this cell. Okay, plus the weight, of course, plus the weight. So this is another visualization of what's happening in the DP table. Okay. So the next question is like, how do I traverse the diagonal, right? Because recall, we want to move over in this direction. We want to move over in that direction. Of course, we need to go like traverse it like this, then like this, then like this, then like this, then like this. Like kind of that's the picture. How you traverse a diagonal, okay, is notice that if you traverse the diagonal, the j minus I is always different by a constant. Okay, so this is like a fancy observation which might not have occurred to you before, but you consider this guy and this guy, the yellow and the greenish color or bluish color. The difference between 3 and 1 is 2. Then same thing, 4 minus 2 is also 2. So somehow they are constant here. Okay, so they are constant here. And so that means we try to increase I. We try to go down the I, and then the j, basically how you choose the j, right? We want j such that it is moving diagonally as well. Okay, so how you do it is basically always compute like by a constant size. In our case here, for the case of this diagonal, our constant is size 2. So we always compute j equals to I plus size. Okay, so anyone lost here? Can I get thumbs ups? I'm scared of losing people here. This is me trying to go through the table up one by one. Need me to repeat what's going on here? This is not good. I don't see thumbs ups. But no one's asking. Maybe presumably so lost you don't know what's going on. Okay. Since no one is asking me anything, but no one is giving me thumbs up anyway, let me just like quickly go through what's going on. So the idea is that here, right? Here I want to fill in this portion first, and I'm curious like, oh, what's the recurrence regulation for one cell over here, right? And you notice that we compute it like this. We compute it using our recursive formulation, and the adjusting the k is basically like considering all the results for one cell. This is only for the line 10 onwards is only for one cell. Okay, so this is why this portion is trying to come up with the recursive formulation. Just fill it up with a recursive formulation. Okay, then okay, this is another example. Then we want to traverse the diagonal because we want to go all the way up towards the target value that we want. Okay, and how we do it is by observing that the difference between the two things are a constant. So basically, if you go down the I, how you choose the j is by adding I to that constant. Okay, that is why this portion is basically for you to try to traverse. As you traverse down the I, you somehow come up with a scheme so that it goes diagonally. Okay, so this is the thing. Then how to traverse diagonal towards the upper right. Basically, we know how to traverse diagonally like that, like from the top left to the bottom right. Now we want to see how do we move this diagonal towards there. Okay, and well, this time notice that just now I considered the difference between I and j, right? This is 3 minus 2, this is 1. The difference is 1. And then over here, the difference is 2, right? And so on. So if this cell, maybe it'll be 3 all the way to n minus 1. The difference between j and I increases by 1 as you move up the diagonal. Okay, so okay, I'm running out of time, so let's see if I can finish. So basically, this part over here is for you to increase the constant difference. Okay, we are always adding the size to I. Okay, so why do I call it a size? Is because you'll see in a bit. So this thing over here, we try to increase it from 2 to n minus 1. And I think someone told me they might get off by 1 somewhere, so you can let me know later which one it is. So I try to increase it, and okay, so this is the full pseudocode, and maybe I'll try to give an intuition of like what this algorithm is doing. Like this is me mechanically doing it from table, but the intuition is that you try to view it. This part over here is trying to compute the base cases, right? Start from the smallest polygon. Okay, so increase polygon over time. So for you to answer size of polygon size 3, you need to think about what's the size of polygon size 2, right? Or maybe for polygon size 5, you need to know the answer to all the polygon sizes from 1, 2, 3, and 4. Okay, so this is increasing the polygon size over time. This part over here is to try all the polygons of that size. Okay, so remember just now that's basically trying to okay, so pictorially, basically it tries from using this side or this side or this side or this side or that size. Okay, so this is all the polygons of that size. Okay, so you try starting from all the sides basically. Okay, this part over here is trying to guess the triangles for that polygon. This is what we have in the recursive formulation. Okay, so the time complexity is the total time required to compute all the cells, right? And well, one cell takes up ON, right? This part over here, it takes ON because we have a for loop basically. Okay, then in total there are n squared sub problems. Okay, so there are ON cubed in total. All right, so okay, I'll skip this part. This is the recursive version. So I'll just conclude this tutorial first. If you have any further questions for me to go through again, we can talk about it after during consultation hours. So bottom up versus top down, usually it's not that different. I used to prefer top down, but for some reason these days I can think bottom up also. But Well, in real life, maybe bottom up, you can have good performance because caching, right? And because the top-down approach in computer science, or at least in programming languages, you need to maintain what we call the stacked frames, and that might be inefficient. Okay. In rare cases, for top-down approach, sometimes it can skip many sub-problems, like significantly skip many sub-problems. So it actually like perform better in a asymptotic sense. Okay, but this is very rare. Okay. So okay, never mind this. So if you want to try implementing this question, there's actually a lead code question for it. I tried it a few days ago, and the tutorial solution works, at least to me. But before you try this question, I recommend like just forget about 3230 for like a few hours and try to see if you come up with the formulation yourself again before you answer this question. Okay, so this is just to summarize like how you DP is trying to brute force carefully. Remember, identify the sub problems, then try to assume that you have the answer to the small sub problem and try to combine them together. The key point here, I think, is that if you have a lot of sub problems and you don't know which one to use, try them all, guess them all. Okay, and that's what DP is kind of like usually doing. Okay, so if you're confused about DP in general, there are tons and tons of resources for DP, a lot of lectures for it, and a lot of questions for it. So I've given some selection for you to try. And yeah, I apologize for rushing towards the last part. I think I might have not explained that part very well, but if you have questions, let me know. Okay, so let me share the slides in the Zoom chat. Okay, so I've shared the slides in the Zoom chat. Sorry for like ending exactly at 10. So thank you very much for coming today. And yeah, if you have any questions, let me know. Nice. Yeah, no problem. I should range to n-1, n minus size. Okay, no problem. Okay, so let's see. Somebody told me the typo is here, n-1 minus size. Let me think, yeah. N minus size. Yeah, maybe that's the case there. Let's see. One, two. Okay, let's say size is 2, right? Go through the recursion tree. Okay, Ken, so someone is asking me, okay, I'll try to see whether there's a typo here or not, but I think the goal here for this question is to try to think how to do it bottom up. Okay, so someone is asking me the recursion tree for question 3. Okay, so maybe I should put the sub problem here as well. Okay. Put it here as well. Let me fix this to J first. Okay, so the recursion tree for this is, let's say, okay, so the recursion tree for this is your compute, let's say we're computing cost of 1 and 4, right? Computing cost of 1 and 4. Then this computes for, we need to do k. Okay, sorry. Let me go through from the top. So this is the recursive formulation. And then the k ranges from 2 to 3, right? K equals to 2 and 3. Because I equals to 1, j equals to 4. Intuitively, what this means is that you have a square, like you have a 4 gone. Okay, so you choose this point. You choose these 2 points. This is 0.1, 0.4. And then you kind of like draw triangles from there. This is k equals to 2. Then this is k equals to 3. Okay, this is like what's happening. Okay, so this part over here, is basically choosing k equals to 2. For k equals to 2, I have CIK, this is CIK, and this is CKJ. Okay, so the other one is, this is also CIK, and this one is also CKJ. CKJ, but for K equals to 3. Okay. Any questions about this so far? Yep. Okay, got it. So the next part is the same thing. We do basically the exact same thing, but the reason I stopped here is because T12 is already base case. Okay, so yeah, that's why I stopped there. It's already the base case. Yeah. But I think intuitively, for me, right, like even if I don't expand the recursion tree, I look why is it n squared, to me at least, is because, well, you're computing cost based on this. There are n choices for this, and there are n choices for this. Like this parameter and this parameter. And you're only computing all the different like 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 2, 2, 3, 2, 4, 2, 5, all the way. So at least to me, that's why like intuitively this should be n squared, even if you don't think about it in the recursive relation sense. Usually parameterize, it depends on the parameters lah. Usually. Okay. No problem. Okay, so well, any questions you have for me? If not, then maybe I'll just for fun go through like the alternative formulation that I had that I didn't have time to go through.
Sorry, can I ask a few questions about the assignment?
Oh, yeah, sure.
Okay, sorry, can I check for in the case of question 2, right? Do we need to account for odd and even n? In the case where n is odd and n is even.
I see. That's a good question. I think a rigorous proof would account for that. Okay, I don't know what the answer scheme is going to be like, but personally, when I tried that question, I didn't think too hard about the odd and even case. But I think how you can like kind of like how to say like consider both at the same time is maybe like you overestimate the actual cost a bit. Like maybe that's one easy way for you to consider both at the same time. But I think a rigorous proof will consider both. I don't know if they expect you to actually consider both even an odd case. But me going through like my thinking right now, right, is that if I was lazy and I don't want to think too hard about the odd and even case for the half, right? For the halving, I will maybe like overestimate slightly, like say, oh, actual cost for both is upper bounded by like something. Like the more expensive of the two. But it shouldn't be too much of a difference. It's just annoying to handle odd and even case because one of them maybe like the divide by 2 is not exact, right?
So okay, then like because they were incrementing I from 0 to n minus 1, do we need to account that in our time like our analysis? Like do we need to account credits for that for the accounting?
Account credits for like incrementing the I, is it?
Yeah, from 0 to n minus 1.
Oh, okay, so don't need to think too hard about the algorithm, I think. Like just think of it in terms of the cost of pushing and pulling.
All right.
Yeah. So and even if you need to account for it, I think you can just like top up a little bit more, like charge it a bit more to like basically twice of whatever you used to pay for like the push and pull and whatever.
All right.
Yeah,
then
but I don't imagine it needs to be accounted for. Yeah, sorry, yeah, go ahead.
Then because they said in any sequence, so do I just show the worst case? And like if I just show the worst case, right, do I need to like explain why it's the worst case?
So okay, what you are saying is, are you like proposing, okay, instead of looking at any sequence, I look at the worst sequence, like worst possible sequence? Is that what you're asking?
Yeah, because like when they say in any sequence, it's a very general.
Yeah,
Yeah.
it is a very general thing. And indeed, like amortization wants us to show that any how to say, like in really, like usually what in amortization, what we want to show is that in any possible sequence, like maybe all pushes or push and pull and halves and so on, or just like keep halving for some reason, any possible sequence, the runtime, the actual runtime is still bounded by some total sum of the amortized cost. Usually that's what we want. So the slightly thing about, I can understand like if you want to argue like, oh, this is the worst possible sequence, right? This is the worst possible sequence. But I would say that usually, okay, just to answer your question, I would think that it's kind of like valid if you can argue for the worst possible sequence, then saying, oh, this is the worst possible sequence, so that's why other sequences are cheaper. I think in terms of proof, that will be valid, but the tricky thing is that how do you show that it's actually the worst possible sequence? And I think that one is the proof can easily like go all the like get messy. Like it's hard. I think it might be hard to be convincing to say that you have this is actually the worst possible sequence. I think that might be tricky. So, but for amortized analysis, the accounting method, what you usually want is to consider basically how you can show that any sequence, that part is by arguing that the bank never goes negative no matter what. So like the part about arguing the bank never goes negative kind of like accounts for all the different sequences out there. Does that answer?
Okay, then for like question 3, right? Like when we do multi-pop, can we always assume that because they say K, right, is the input, can we always assume that the size of stack is more than or equals to K?
Okay. I forgot the question exactly. So like if the other people still in the consultation can correct me. I think the multi-pop says that basically if K is less than the size of the stack, sorry, K is larger than the size of the stack, then you just pop as much as the remaining elements of the stack. So if you have K equals to 10, and then your stack only has 2 elements, the cost will be just the cost of popping those 2 elements. I don't know if that was, I vaguely remember that was the part of the question.
Okay, because I think like if they just pop the remaining elements, I think like it affects the potential. Yeah. Yeah. So then for the final answer, do we like can we just say that it's less than a certain number, or do we have to have the big O function? Because they said they want to find the total cost.
Yeah.
So can I just say, oh, it's less than this, or do I have to present it in a big O function?
Okay, let me recall the question. I know he changed it yesterday, right? Change it to the total cost. CD assignments. CD. 1 second, yeah. Let me open the question first. Okay, so yeah, it says here, right? If size is stack is smaller than K, then pop the top K object. Oh, sorry, popping the entire stack. Amortized cost. Okay, so this one is the total cost, right, of all the things, all the n. Let me see. Actual cost. I think I would imagine exact is possible to express. But let me see. I'm not too sure. I'm not too sure actually whether they want big O, but usually for amortization, No, I can't say that. I can't make claims about the answer. I'm not too sure if you can give exact or like the upper bound without the big O. I think that will be somewhat better for this question. But does it change drastically if you use big O? Because I mean,
I just say either it's less than this, or I just big over the whole thing.
yeah. Right.
Like I just want to ask, like normally, like in proving, right, for this mod, which one is more preferred? Yeah.
Yeah. So let me see. I think this one best to ask Prof because I'm not too sure what he wants for this particular question. Usually when I think about runtime, like usually I smack some big O's if they want the runtime or like space complexity of the algorithm, then I'll put a big O. So for individual costs, amortized costs, I will say that it's big O something. But if it's total cost, because I very rarely talk about total cost. Frankly speaking, this is like the first time like I'm asked the total cost for something. Usually the only time I discuss total cost of something is in tutorials where we discuss like why the amortization works. Like that's the only time I use total cost. And showing that amortization works because of the total cost is something, usually we don't use the big O for that. Or at least if you okay, so let me open the slides from last week. Second, yeah. The cons of having a lot of slides is it takes a while to load. Okay, potential method. Yeah, usually I only like all this term is that I use the total sum without any big O yet, but in the claim, okay, so usually in the claim, we claim that the total sum is big O something. The total actual cost is the big O something. Then because CI upper bounds TI, so how it looks like is sum C, sum true. So by saying that sum C equals to O of Fn, then you imply that this is this, right? But I think you can, if you already have the exact, right? I think you can keep it as exact for total costs. Yeah, I'm not too sure, sorry. Might be best to ask Prof what he wants.
Okay. Then like yeah, so like for multi-pop, can I assume the size of the stack is always more than or equals to K? Because for example, I think when it's less than K, right? And then delta phi will change, and then the amortized cost will change also.
So sorry, I don't follow the question earlier. You said assume the size of the stack is smaller or greater?
Greater. That means whenever I multi-pop, right? For example, I multi-pop 5, like there will always be more than 5 items in the stack for me.
I see. I do not think that might be a reasonable assumption for the reason that he explicitly mentioned like popping the entire stack if the size of the stack is smaller than K. Like he explicitly said that he said that, oh, if size of the stack is smaller than K, then I'll pop the entire stack. So because he mentioned this in particular, I imagine that he has in mind that you can call multi-pop even on an empty stack. Like starting from an empty stack, I'll call multi-pop of like 100, 5, 2, 3, 4. But it does nothing because the stack is empty, right? But yeah, so to answer your question, I don't think that's a reasonable assumption because of this part.
Then is it okay if the, for example, multi-port, right, the delta phi will differ?
The delta will be
Will differ because K
yeah.
will.
You can use like a minimum function, maybe a minimum of the two, something, or maximum of the two. I don't know which one, which direction.
Okay,
I'd like
can.
to make it consistent lah, but different. Yeah, it can be different, right? Delta can be different, but it can be simplified by using like a minimum or maximum probably.
So it's okay like for a certain operation like the delta phi differs lah.
Yeah, it's fine.
Okay, can. All right, thank you.
No problem. Yeah. Oh right, sorry, I forgot. He wanted to ask about the no, some other person wanted to ask about the cut and paste, right? Is still here? Let me open up the slides. Okay, so sorry, I forgot. Week 7? Is it 7? No, week 8. L08 dynamic programming. Okay, cut and paste argument. Okay, so okay, let's see. Let me see which example would be good to go through. Okay, maybe I'll just give a overview of this, like in the case of LCS. The cut and paste argument is that, okay, so let's remember, right, LCS is to find the length of the common subsequence. Okay, so you have two subsequences. You have two subsequences, right? And you want to find the longest common one. So like, for example, this is maybe AB, C, C, D, D, and this is some garbage, Z, X, Y, W, A, I don't know, 1, 2, 3, some garbage, okay? So it doesn't match, it's not the common subsequence. So you want to match A and A, B and B, C and C, D and D, okay? So basically, the longest common, the cut and paste argument is saying that, okay, so we know the rough idea is that, let's say we know that the last guy matches, right? They are both A and A. So this guy is A, 1. Basically, the length of the subsequence, we contribute 1 to this thing. We contribute 1. Then let's assume the cut and paste argument is saying that, okay, so let us use something that is not suboptimal. We prove by contradiction, right? Prove by contradiction by cutting out like a suboptimal answer with an optimal answer. Let's assume that, okay, I'll just give numbers, okay? Assume suboptimal is maybe like 5. Okay, this is, let's call it A, like this entire thing, let's call it A. Optimal of A is 5. Then maybe optimal of A is like, I don't know, 7 maybe, for example. Okay, what the cut and paste argument is saying is that if you can, this bigger problem, let's call it a big. Okay, B for big. Okay, so if it says that if the big, you can form it by 1 plus suboptimal of A, right? 1 because like you have match, okay. So 1 plus suboptimal of A, this is 5. The argument is that you cut out the suboptimal answer, and then you place in the optimal answer. Okay, so remove the suboptimal answer. This is 7, and then suddenly you get a better result. You get like 8. Okay, so to go through from the top, the cut and paste argument is usually to prove the optimal substructure, where you say that, okay, I want to solve for big. I want to solve for the big problem. I break it into two. I break it into the last part that matches plus a smaller subproblem A. And I claim that, hey, I might be able to solve this using the suboptimal version. Using the suboptimal result of A, I can reconstruct an optimal answer for big. Like, is this claim true or not? Okay, we prove that by contradiction using the cut and paste argument. Suppose it is actually the case, right? So suppose the big problem can be solved optimally using the smaller suboptimal A plus 1. Okay, well, what I can do is that I can take out the suboptimal answer. So I can take out, okay, so this guy over here, this suboptimal answer, I take it out. And I replace it with the optimal answer to A. By replacing the optimal answer to A, we get an even better answer. We had claimed that we can solve it without using the optimal. Using some suboptimal answer, then this is best already. Like, the big is the best answer you can get already using the suboptimal problem. That was the claim. But we prove otherwise using the cut and paste argument, where you take out the suboptimal answer, paste in the optimal answer. And your best answer, there is someone who is even better than the best answer, contradicting that we started off with the best answer originally. Does this make sense?
Yeah.
Okay.
I think I got it. Yeah.
Okay.
Thank you so much.
No problem. Okay, any other questions?
Not really a question, but the the question for the algorithm, I think just now you mentioned there might be an off by one error somewhere, right?
Yep.
Yeah, I was thinking, is it line 6 is supposed to be n minus size instead of n minus 1 minus size?
Yeah, I think someone mentioned that as well. So
Yeah, because I was looking at the diagonal, right? If I'm not wrong, line 6 is supposed to basically try all the elements along that diagonal, right? So if you do n minus 1 minus size, you just stop at the like if you for the first diagonal you compute, right? It's going to stop at I think 3, 5 was it?
3,
It's going to stop at 3 n minus 1. Yeah, it's going to start at the square. It's never going to compute 4n. So
yeah, might be. Yeah, I think you might be right. So let me see. Let me think through again. So if I goes to n minus 1 size. Yeah, you're right. J will always stop at n minus 1. Yeah.
Right.
Yeah, I think so. And that's weird because I'm pretty sure I submitted the code using n minus 1 minus size. So let's see what goes wrong there. Like, that was accepted in LeetCode, but I wonder why. Oh, I did use n minus. Oh, okay. The reason it worked for LeetCode for me is because the table here is one indexing. The table.
Oh.
Yeah. Here is 0 indexing. Yeah, no wonder. Yeah. You're right. Yes. So my bad.
Oh,
so
okay. Everything makes sense. Okay.
Yeah, no wonder it worked for me. So because I implemented it, then I was like, how come there's an off by 1? Yeah, then you're right. Off by 1. Dear, I have to change everything. Oh,
actually, in terms of isn't it only this guy which has the issue? The rest is fine, I think.
the rest is fine. Yeah, as in, like, I changed everything as in like this slide appears many times.
Oh.
I had to hand change like
Well,
at least 10 slides.
that's my replace.
Yeah, you're right. Yes. DT.
Right.
That was, yeah, I miscalculated the time taken to go through.
A bit of a kickdown moment.
Yeah, bit of what?
A bit of quite a bit of a movement there. I understand.
Yeah.
Yeah, actually, I think other than that, I got nothing else already. Okay,
Yeah,
so
thanks a lot. Yeah, thanks a lot.
right, I'm gonna head out first. Bye.
All right. Yeah. Will there be a need to fill the entire table in this case? So someone asked, will there be a need to? So you're asking like, for this case, I'm not sure what you mean by the entire table, but for this particular algorithm, you only need to fill like this region. You don't need to fill this part. You don't need to fill. It can be anything. Yeah. Is this what you're asking? Yep, correct. This is all you need to fill up. Like this, in this particular case, you can fill up from this region only. You fill up this region only and you should be fine. Okay, so naturally, like the analysis means that you don't need, that's why I say ON squared cells. Okay, I'm just upper bounding over all the cells. But
First, I was confused by the runtime. Yeah, then I was like, n squared cells. Wait a minute.
yeah. That's why I put ON squared cells actually.
It's always, yeah, okay, to be fair, it's n squared, like half of n squared.
Yeah, correct. So it's like n times n minus 1 over 2.
But ON cost to compute, is it?
The ON cost to compute, well, it changes over time, right? Like here it costs like maybe n. Here it costs n minus 1. Sorry, my bad. Sorry, different. So different diagram. So it costs ON cost to compute because I'm upper bounding by this worst case over here. This guy needs to compute this and this, or this and this. Sorry, not all. Like I need to compute this and yeah, everything lah. So that's why this takes n. This takes n time, right? Then, but for other cells, it might not be the case because like, sorry, the table is a bit small, but like this guy over here only needs to compute like here and here. To make analysis easier, yeah, this is probably like just 1 or 2, right? Like just compute this guy and this guy plus the weight, and you call it a day. So this takes like more like 01 for like constant time for this particular cell. But the reason I upper bound it by ON is, well, makes analysis easier lah, because I think it's hairy to reason about to like +1 +2 +3. Actually, you can if you are very careful about it. Probably, I can't imagine actually, but the reason it's okay to upper bound it by ON for everything, you might think like, oh, it's wasteful or not, right? But remember, we are computing over over all the sub problems. So eventually you end up with probably something like, I have n cells, right? Okay, simple case. Let's say I only have n cells. Let's say if I only have n cells, I'm only computing this region. This is already like 1 + 2 + 3 + all the way to n, which we know is ON squared, right? By sum of AP, n times n minus 1 over 2. Or +1, I think it's +1.
So just to confirm, the n comes from finding the mean of like n entries you need to consider. Is it something like that?
Yes. Finding these entries, finding j minus 1 entries to be precise.
J minus 1 entries. The basically
plus minus 1, I think I'll buy one somewhere.
Yeah, each entries. Then you must find the minimum out of all of them. Then you put the minimum into that current question mark slot, right?
Yes.
Oh, okay.
So
okay.
that's where, and you know, like we just upper bound it like, oh, let's say this is ON. This j minus 1 is ON. The difference is constant upper bound n. So
just the algorithm by itself very hard to follow.
Yeah, understand. Like,
and one of the things I had was when at the very first question, right? They tell us all the stuff like there's I prime, there's J prime.
Yes.
Yeah. Then I was wondering, I was stuck because I thought we had to use it for notation, not like we had to just like come up with some random point K. It's like, oh, this is your point, third point,
I
and then you
see.
can use it as your third point to do IJK.
Yeah.
Then I
Yes.
was like, what? Because I thought you were supposed to use like the notation you kind of give.
No. It just means it's a small poly. I think the one given out in the tutorial slides even more confusing. Like here, I tried to give it.
Because the one in the tutorial slides tell me like I prime J prime. So I thought like we have to fulfill the condition that J prime minus I prime must be less than J minus I, which is basically it's a smaller polygon with like some less points, right?
Yes.
So now I was just wondering why how we know that we can just come up with this new K.
Yeah, let's see.
At least the question in the slides was very confusing.
Yeah. Like, is there a question for me, or are you just like wondering?
I was wondering how you know that you're supposed to come up with a new point K.
Yeah. I guess the way the slides, maybe like the tutorial slides given, was perhaps the one that was misleading. But like usually when we tell you because we try to guide you, but I guess the way we try to guide you made it confusing. But usually when we give a DP problem, they will just like smack you, give you, oh, this is the polygon, try to minimize the cost. Okay, so you have to think about the sub problems yourself. And how you think of the sub problems is, as I mentioned earlier in the tutorial, we try to like guess like one particular case. Okay, so guess this one particular case, but it can be anything. Guess what you're guessing is which triangle we should choose for an edge, this edge, right? So you can try everything that you see here. You try everything that you see here. So at least to me, that was how to come up with the K lah. Because you come up over everything here.
Because based on their notation, right, they were saying I to J, right? And Putra and I were discussing, right, must it be sequential? Because if you look at the slides, they said something like P1 to Pn store in that array, then Pi to Pj. So we thought like the I to J, right, must be sequential. So it's like
but it is sequential, no? Like
it's like a sequential try, right, of everything in between like I and J, right?
Yes.
You fix I and J and then you just spam try everything else, right?
Yes. Yeah, I think the question might need more, like they need more clarification of whether there's wrap around. Like I to J, does it mean like you can go around past back one or not? But I think can, but it's just not that clear in the question.
Yeah, but the rest of the question still okay.
Yeah. Let me fix all this now.
the KJ.
Yeah. Sad. It's appeared so many times.
That's Control F CKI.
Control F. Yeah, I guess that's possible, but it's okay. I'll just go through everything one more time and see. Okay, this is fixed already. Okay, nice. Is this fixed already? This is not fixed. Yeah. Any other questions? Like, well, I guess the slides now.
That's it for me. That's just the idea of not using I prime J prime. It was just a bit confusing, and like the last part of the algo was a bit.
Yeah. So if you have any questions, just let me know again.
Yeah. I think for now, no. I think that's it for me. Thank you.
No problem.
And bye.
Okay, so that concludes this week's tutorial. Yeah, so I'll stop recording now.